Hi, everyone. I wanted to, so I'm going to keep the talk. So the talk is supposed to keep by my student, but he now working at a company. He cannot do that, so I replace him. And so that's the reason that I will need to quit after this because I have another presentation to give for another person in the other workshop. All right. Can you hear me well?
Yes, go ahead.
Okay, good. Yeah. Okay. So now let me start with the introduction of the problem that we are working in this work. So we have been working with one of the problem in smart grid for many years, and one of that is like the demand side management, where specifically we have so we consider the smart home situation where an owner have many appliances that could be turned on or turned off automatically, right? So, and the problem is that we wanted to provide the owner, the user, a schedule that optimize let's say, the cost or satisfying the user preferences. So the general problem is to schedule the appliance that we wanted to incorporate the human preferences. And user usually have preferences on how and when to operate the device. And the first problem in this is that the first issue is that the precise preferences are hard to come by. So in the previous work, we try to solicit the preferences of the users, but we realize that asking the user to fill up, for example, a matrix of 20 by 20 is already hard. But then when you have more appliance, it's so. And so lately we have been using like a probabilistic distribution to represent the preferences of the user. Now, when you don't have the precise preferences of the user, then the problem arises that the human and the scheduler interaction can come up like the user would be interested in asking the question, why do you turn on? Why is this device is on at this time? Or what if I turn on this device at that time, and so on and so forth, right? So in this kind of situation, the explanation, we need to generate the explanation and explain it to the user. Now, the problem here is that user of such a system are usually non-expert. They would not understand the formula that you present to them, and so on and so forth. So in the past, so in order to do that, we wanted to, so basically what we wanted to do in this paper is to show that we wanted to explain to the user, but generating by generating the explanation in natural language. Okay. Now, we have done some work in this direction previously. So previously we was like given that we use logic programming to represent all the information that we have. So we can and work with ontology before. So we have a framework to generate a natural language sentence using annotated ontology. And then another one is to generate the NLP, natural language sentences, using grammatical framework. And in this paper, we wanted to, so we attempt to use language model to generate the sentences. So the previous approach, it requires certain effort from the ontology description and so on. So I'm not going to talk about that here, but if you are interested, we can talk more about that later. So what we do with that? And so Now I wanted to give you a background, like what do we mean precisely by the scheduling problem and by the language model that we try to use. A scheduling problem is a tuple, like a set of appliances, the description of the energy consumption of each of the appliance, the time slot that we need to schedule this appliance for, and the cost basically energy cost is time dependent. So we have this vector of the of cost, and then the permissible load, a vector for the house, so they may be different at different time. And then the dependency matrix, so that encodes the information, like whether certain appliances have to be on before the other one or after the other one, or they can be operate in parallel or not in parallel, so on and so forth. And when it is new, that means that there's no dependency between the two of them. We assume, or we represent the user preference using the probabilistic user, it's a tuple like this. Like we have a preference matrix, and for each that corresponding to the number of appliance and the number of time slots, and each of the cell here is the Nij, the preference matrix. Nij is a normal distribution that with a given standard deviation and the means, and then alpha here is the cumulative satisfaction threshold. So that is an input from the user, and then the probability threshold for the acceptability of a schedule satisfying alpha, and then it's a number of so basically the cost, the cumulative satisfaction, and the probability of the test. So then here, like we call a scheduling problem, the smart home scheduling problem is a pair where P and C, where P is a scheduling problem and C is a probabilistic preference over P, right? So here's a simple example of like a situation where we have 4 appliances, 3 time slot, and that is the cost. And then this is the distribution function that say that at this time slot, this appliance should be on or off. So this is that. So what and then here is an example of this of the solution for this problem, right? This is on at this time, on at this time, so on and so forth. Where here we assume that each device is turned on at only one time, and it needs to satisfy all the constraints that we've shown, and the total minimized cost, for example. So here, how do we define the cost of the how do we define an optimal schedule? Is like if we have a solution of this problem, and then we generate we define a normal distribution for a schedule H as like given by this mean and this sigma, right? The mean and the standard deviation. Basically, it's the summation of the standard deviation and the mean and at each of the. So Hij here is on and off, so it's 0 or 1. So then we can calculate this value, and then we say that the schedule satisfies the constraint in the scheduling problem. The hard constraint is this one. Like if one is before the other, then basically that implies that the other one. So if I is before J, then this have to happen, and so on and so forth. And then when this power safety thing, so the load have to be satisfying, and then the user preferences, the value of this normal distribution have to be greater than or equal beta here, the threshold that we want, and the cost efficiency. And then when we have we define the optimal solution as basically over the space of all the solution. And I will not focusing on the computing the optimal schedules, but so we have developed different methods to solve that problem. Now the focus of this paper is how to generate the explanation from the solution computed by either of the approach, right? Assuming that we can use the CSP or solver to solve the problem, or the sample average approximation. How do we want to do that? And so in this paper, we focusing on using the language model to generate sentence satisfying. What happened is that very quickly about language model. So basically, it is mapping each language model basically assigns a probability to a sequence of words, and then from that language model, we can basically calculate the probability of the word friends. For example, here I have it like I enjoy working with Pi, and then I can complete the sentence by calculating the probability of friends, dog, and so on and so forth, and getting if we using the greedy approach to generate sentence, or depending on the probability that we calculate here, we can basically complete the sentence, right? So there are two things that we need to do in this subject. So in here, how to generate the explanation. So first of all, what is an explanation? So if we represent the problem as this, as given like a matrix like that. So when we wanted to explain the question such as why is this device turned on at the time, and then we need to explain like to the user that the preferences at this point is given like by this distribution, and then if you do this, then the total consumption of the energy is optimal, for example. So how do we? So there are two things that we need to do. First of all, we need to find the content of the generation, and how do we do that? What we're going to do is we wanted to generate the content of the explanation using answer set programming. And so here in this paper, we focus on the two questions that a homeowner or the user is often interested in. It like, why is a device D or a set of device D1 to Dn is scheduled to turn on at the time T? Or why is the device D scheduled at time instead of the time T2? So this is a question of like, what happened if I turn on, this could be answered by what happened if I turn on this device at the time at a different time slot, for example. So to compute what needs to be explained to the user, we use answer set programming to extract the information to these two questions. And then basically we can encode. So this is how we do that. We basically create a program that calculate for us what it to say. So the encoding of the problem is very simple. Like how are the dependency of the of the device, and so this is the hard this line here encode the hard constraint, right? And then this is the maximal energy consumption that it allowed like by the user, and all this, right? And then here we have like how to calculate the energy consumption at each of the time slot, and then here the user the schedule, the preference of the user, and all this, like the total cost. So we calculate that. Now this program given an answer set, given a schedule and the specification of the problem will give us the set of atoms that satisfy certain, like if we have a question, If we have, so we define that, right? If we have a question, then we can basically like extract the information, the atoms that are related to that question. And so we have a collection of atoms that could be answered, right? And we associate the ASP atom to the meaning, like if the cost of this, the electric cost at time t is this, so this is the time cost, and then the device consume this much of energy, and so on and so forth. We have this kind of like predefined information for each of the atoms, right? Now, when we get this content, we will present the sati. So basically, if the user asks a question, why is the device turned on at certain time, and then we present the satisfying constraint that is related to the device, and the energy threshold is satisfied. And then for the second question, we identify the difference between the two potential schedules, right? And so now, as I mentioned at the beginning, we wanted to use language model to generate a sentence. So the aim is, so first of all, then we have to have a language model for the collection of atoms from the schedule, right? The key question here is, how do we get the data to train the model, and how do we train it? So in this paper, we apply a very simple, so we make use of the pre-trained language model called GPT-2, and that is available for us to, and fine-tune it with the training about the smart home scheduling problem data. The training that we did is like done using the transformer. We get, so from GPT-2, getting all the data, and so we call the new model, the new language model is GPT-2 or SPS. So so this is the model that we can generate, right? And so in order to generate the data to train the model, what we do is so first of all, let's observe that this is a kind of standard. The first line here shows the standard pattern that we have to enter to the transformer, right? So we did not use this part. This is the classification. We don't need this, but the part one is a description of the atom, and the part two is the natural sentence for the meaning of the atom. So, for example, we generate this, like on 120 has parameters 120 turn on, right? And then what is that? The natural language sentence for the meaning of the atom for the list described. So here we have on 120. So we say that this is the device one is on at the time slot 20, right? Or here, like this collection of atoms, like 6, weight 1155, and so on and so forth. So here, what is the sentence that we want the language model to generate is at time slot 1, 2, 2 device turn on, and the total energy is 12 kilowatt. Right? So we use basically ASP to generate all the atoms for the training, and like have a script that basically generates this pattern and enter and then use transformer to generate to train the model, right? So here this is a program that we use to generate all the possible atoms in a problem. So note that because of GPT is a very rich pre-trained language model already. So what we observe is that we don't really need to, if say for example, we have the problem that talk about maximum energy of 100,000, for example. We don't really need to generate all of the atom that it represents using when we have this maximum energy threshold like 100,000. We can use like 50 or 100 only. We don't really need the whole lot of that, right? So this one basically generate all the atoms that we can generate it, and then create the sentence as we have here, like this pattern, and then keep it to like so this kind of pattern here, right? And we use basically the transformer and GPT to generate, so to get out. Now in our problem, for example, we have this problem, and then we have a schedule like this. We then use it GPT-2 that fine-tune program, a fine-tune language model to generate the sentences that. So the one thing that we observe is that one is that we use so after we have the language model, we can generate the sentences. We use a greedy approach to generate that. So we basically just, if we have a sequence of words that then what is the next one is going to be like so we take the maximum, the one with the highest probability. So what we observe is that, like say for example, this on 1-4, it explained as like this device one is on at the time slot 4, but then the language model generate also like trailing words like this part, for example. Had it not been there, it would have been perfect, for example, and it may be repeated like this. So this is what we get, and it, on the other hand, for example, it does do what it does is that it generates sensible sentence, but not the best sentence that possible that we wanted to do or to have. So that is what we have so far. So it's conclusion that I have here, like we show that using language model to generate natural language explanation in a specific AI application is feasible. The sentence that we were able to generate is more than just a template that you could put in. It is nicer, but what we observe is that there are still things that could be done, that could be improved, and we're looking forward to that is the next thing that we wanted to try to see whether, for example, like this, like how can we remove this one, whether there is any strategy from the language model, like natural language generation, that we could apply so that it doesn't have this part, or whether we have trained the fine-tune the GPT-2 with too less data, and so on and so forth. That is what we are trying to do currently. So I stop here and have listen to questions.